is the assertion that X is faster than A, B, and C, and then in the small print, there's some context in which that is true. And the key, if you're doing the marketing, is to get people to forget about the context. You want them to treat this statement as a universal truth. X is faster, X is better. So the goals are, in addition to hoping that context is lost, is you don't really want to explain why, because that's too much information, and that might distract from the attempts to get the context to be lost. There's some risks in doing this, though. In some cases, you might not know why X is faster, and it might be faster for not good reasons. You might have made a mistake in running these tests. Something I did that's embarrassing, although I owned up to it in public. When MySQL version 8 came out, I ran a lot of tests with it where SSL was enabled for it, but not for the previous versions. And so the CPU overhead from doing encryption and decryption was really bad for performance. And I blamed that on MySQL 8 when it was really just a configuration problem. So I ended up having to correct some somewhat snark-filled blog posts that I had written, and hopefully I learned a lesson from that. Another factor is that if you're testing X versus products A, B, and C, that as that list gets longer, if you go from A to A, B, and C to A, B, C, D, E, it's hard to get expertise in all of those systems. And so I tend to have less faith in comparisons that include too many systems, just because the expertise in all of those systems is hard to get in one place. I see a lot of bold claims about new systems, and in many cases, these new systems are fascinating. Some amazing work is being done to generate this performance, but the claims are usually of the form, my database can do millions of writes or queries per second per node. And having spent too much time in production, which was a wonderful education, I'm left with some more boring or mundane questions. The first one is, do I need that many writes or queries per second per node? At what point do I stop needing more queries per second per node? Assuming I do need that much, the next question is, does my network support that? It's one thing to have clients co-located in the rack with the database server. It's quite another to have that workload fan in throughout the data center into one node. The amount of networking hardware changes, the demands on networking capacity change dramatically. Assuming I have the network, the next question is, do I have replication that can sustain this? I'm likely to have something like synchronous replication within the data center, which would be latency sensitive. And then I'm going to be doing some kind of asynchronous replication on the wide area network, which will be bandwidth sensitive. Assuming replication can sustain that, can I archive the replication logs at that rate? Let's say that this is writing a gigabyte per second per node. I'm generating replication logs at a gigabyte per second per node, and I have to store them somewhere, potentially for days or weeks or months. And then finally, is backup possible at that workload rate? And by possible, both logical and physical backup. And do I have enough spare capacity on the server handling that much, that many writes per second? Do I have additional capacity to process the backups? Continuing with this focus on X being faster than Y, I think it's overstated. X gets more throughput, or X has better response time. Again, At some point, I have enough throughput per node. I have good enough response time. I'd like to see more focus on assertions that X is more efficient than Y. And this is something I spent many years working on with MySQL at Facebook. Get good enough QPS, get the QPS and the response time that your workload demands, but then optimize for efficiency. So, X using less space, less storage, is a really big deal. You're buying storage by the gigabytes. With EBS, doing less I/O, both reads and writes, is another important deal because you might be paying by the I/O per second. Using less RAM. RAM costs a lot, not just in money, but in power and space. Trying to use less CPU, another goal, or less networking. The last thing, this X lets operations sleep at night, it's not as big a deal as it used to be. I started working on MySQL in 2006, and there were quite a few problems that woke people up at night. With the rise of cloud-native databases and with the rise of database as a service, well, the problem has now been moved to the teams operating these services rather than the end users. So my path here, we had a large tier running uncompressed InnoDB at Facebook. So this was web scale database. And there was a demand to use less space. So the size of the hardware had to grow not as fast as both the data and the workload. So we had to figure out how to cut back on hardware, and the real thing was storage capacity. We started using NAND flash, we wanted to use less. So InnoDB upstream had a compression feature that was marketed for read mostly workloads. We made it performant for read-write, contributed the code upstream. Appreciate that the InnoDB team worked with us, and it compressed the tier in half, which was really big deal. That maybe we made a mistake by doing it all at once rather than incrementally, because soon after that there was a demand, more compression, and so we had to come up with rather than incrementally delivering the previous compression win, we had to find management wanted another improvement. So I spent some time evaluating WireTiger, TokuDB, and HBase. Concurrent with that, the RocksDB project started, and I wasn't on the project initially. I tried it, and it was slow, and I did not debug, and that was a mistake on my part. The slowness was a bug in the Linux 2.6 kernel in the mutex used by virtual memory subsystem. When the database was larger than memory, the page fault handling was just too slow. So separately, the RocksDB team stopped using mmap. I reevaluated it, and it looked performant enough. So we started the MyRocks project, which was a RocksDB storage engine for MySQL. Eventually, that compressed the tier in half again. So now we are 25% of the original size. Huge win. But this created another problem. We had servers that were suddenly using half the storage that they used to use, and so that was kind of seen as a waste. So there was an effort to consolidate workloads and double the logical database size on a node and double the workload on a node. And suddenly we went from not having many CPU utilization problems to being confronted with servers that were using too much CPU. So there was a bit more work following from that. But my summary of RocksDB is best space efficiency. So the least space amplification. And for many people, this is a really big deal. I will claim better write efficiency. So it's not the best write efficiency, but it's certainly usually significantly better than a B tree. And then good enough read efficiency. With RocksDB, you're going to use more CPU, but you're going, in return, will get significant savings on I/O and storage. So we had internally, while the RocksDB project was starting, there was still a team working on compressed InnoDB, and we had to figure out how to get these two teams to talk to each other. We did not, well, I wanted to limit the amount of benchmarking between the two projects. Just one team claiming, hey, we get more throughput, doesn't advance the discussion. The context is we needed performance with efficiency. So at a high level, the RUM conjecture is, pick at most 2 from read, write, and space efficiency, but you need more granularity in that description. So it's, let's split reads into point read and range read because their performance is different on an LSM, and then split read and writes into both CPU and I/O components. So we treat the CPU overhead separate from the I/O overhead. And again, translating this to RocksDB, it tends to use more CPU in return for using much less I/O and much less space. And from my experience, the read I/O penalty, so the doing more storage reads, that tends to be overstated with an LSM, but the CPU overhead from the LSM-Tree doesn't get enough attention. So with the LSM, we need to think about optimizing or tuning for CPU overhead, not just for minimizing I/O. I consider myself fluent in 4 storage engines: WireTiger, RocksDB, InnoDB, and now Postgres. And so at a high level, when I'm tuning, I ask myself some basic questions. The simple one is usually how much memory can be used. And hopefully that's just set for globally rather than per component of a storage engine. More interesting is how much CPU and I/O can be used by background processing, and how do I configure that? By background processing, I mean things like checkpoint and page cleaning. And my preference is that I set CPU and I/O limits once for the entire engine, not per component, because if I'm tuning this per component, tuning checkpoint separate from page cleaning, I'm likely to end up where I'm either oversubscribed or undersubscribed the hardware. Writes create debt or unhappiness for a database engine. So, how much unhappiness does the database engine tolerate? How much debt can build up? And finally, when there is too much unhappiness or debt, what does the database engine offer to shape workloads so that the debt creation gets throttled in a smooth fashion to keep the database from falling over? Another thing I get from dealing with production is, I appreciate the time I spend reading academic papers and attending conferences, but a lot of the focus is on making things faster and making significant advances to algorithms. When you understand workloads and hardware, you can be clever. In production, while there are improvements that can be made to algorithms, those usually take a long time to arrive. And so a lot of what we do is we make things less slow, which I guess is a variant on making something faster. So a lot of time is spent trying to figure out how a database or a storage engine behaves to a workload, and then try to use clever tuning to improve things. I spend a lot of time thinking about how to make a database engine fall over, looking at high stress workloads. The high stress workload might not represent the steady state workload that shows up in production, but it's likely to be an outlier, and the outliers frequently define the user experience. Those are the things that cause outages. So you need to understand how the database engine handles the high stress. And a lot of this comes from doing I/O. Storage is fast and much faster than it used to be. So the storage engines we use are either being rewritten or enhanced to keep up with fast storage. RAM is expensive, and given that storage is fast, let's be more reliant on fast storage and not try so hard to cache the working set. So with an LSM, with a log structure merge tree, the obvious way to make it fall over is to cause compaction stalls. So to generate writes faster than they can be compacted. With a B tree, focus on workloads that are for which the working set is not cached, workloads that are write heavy. When the working set is not cached, you're frequently evicting dirty pages that have few modifications to them. So the write amplification can get really bad. The worst case write amplification is the size of the page over the size of the row, and that can frequently be larger than a factor of 100. Trying to make this more concrete now for tuning advice for both InnoDB and MyROX is, whether you're in the position of you want to make InnoDB or MyROX look better or worse, there's a few things that you can do in either direction. And in both cases, using the default configuration is likely to lead to lousy performance. With InnoDB, it has a 16K page size by default. Shrinking that down to 4K will cause problems. To get better performance from InnoDB, it's pretty simple today. There's this feature called InnoDB Dedicated Server. When that is set, it will magically figure out most of the options that need to be configured. And there's not much tuning you need to do beyond that. For write-heavy workloads, the performance is highly dependent on the size of the redo log. Larger redo means less checkpoint I/O. So dedicated server will set that, but you might also want to increase beyond what it uses. And then consider setting the I/O capacity options to let InnoDB know how much I/O your server has. For MyROX, it's all about the compaction stalls. And the key to compaction stalls is the CPU overhead for compaction in levels 0, 1, and 2. And so if you can increase that CPU overhead, you increase the compaction stalls. If you decrease it, you decrease the stalls. Using compression for all levels of the LSM-Tree mean you're doing decompression and compression in compaction for levels 0, 1, and 2. That will lead to more stalls. Changing the LSM-Tree shape so that the size of the level 1 is much larger than the size of level 0 will increase the compaction overhead from level 0 to level 1, and that will also cause stalls. A few other things you can do. MyROX isn't able to figure out how many CPU cores the server has, so there's an option, max background jobs, to set that. And then block cache size can also be set. RoxDB uses buffered I/O by default, so this is not as important. When I think about tuning, my experience is that there's too many options. Most of them don't matter for most workloads. The challenge is it's not easy to figure out which options matter. That can take a lot of time. Something I think is true but not widely appreciated for stalls in a log structure merge tree. RoxDB definitely has improvement in shaping workloads that write too fast. How it throttles workloads is probably something that can be improved. But the stalls that show up with an LSM tree are usually happening at write rates that would make a B tree fall over. So it's not always an apples to apples comparison. A bit more detail on the L0 to L2 compaction bottleneck, showing that the CPU overhead is the issue. There's a few key points here. One is that compaction from level 0 to level 1 is single threaded, and it consumes all data in level 0 and all data in level 1, merges that, replaces that output into level 1. If you're using compression and if you're using compression, then compression and decompression latency shows up on the critical path here. The overhead from writing and waiting for data to be durable on storage also shows up on the critical path. And somewhat surprising, the overhead of creating bloom filters during compaction can be an issue. So further in the talk, I have slides that explain all these configurations that I've labeled. But in the table here, X3 is the basic configuration. And there's no bloom filter. In this case, there were no stalls during the workload. And the number of wall clock seconds for compaction into the L1 and into the L2 is listed, and it's about 4,000 total. Configuration X4 added a bloom filter, and the stall percentage went from 0 to 30.7%. And the wall clock time for compaction from L1 and L2 was also more than double, just from adding the bloom filter. Configuration X6E uses a bloom filter and increases the size of the L1. Potential benefit from that is to decrease the height of the LSM tree, but the cost is more write amplification from L0 to L1. And now the stall percentage increases from 30% to 41%. And again, the wall clock time went up for compaction. Then starting with configuration X4, enable compression, which is configuration X8A. Using LZ4, which is a lightweight compression algorithm, stall percentage went from 30% to 35%. Configuration XB is the worst example. That uses zlib compression on all levels. The stall percentage now goes up to 73.6%. And the wall clock time is greatly increased. Configuration X8C does Z standard compression for all levels, much less CPU overhead than zlib, and we see the benefit in reducing the stall percentage from 73% down to 50%. And then finally, my recommendation, only compress the max level with either LZ4 or Z standard, and we further reduce the stall percentage. So the key point here is just showing that the CPU overhead of compaction in level 0, level 1, and level 2 determines whether there will be stalls. If we can reduce that CPU overhead, we can reduce the stalls. I did a lot of tests. I did about 250 tests for some of what I'm sharing here. Some took hours, other took days. There were a lot of machine time. I used DSI, which is the topic for the talk that follows me. I used two benchmarks that I frequently run, insert benchmark and link bench in both IO and CPU bound setups. Insert benchmark does inserts and range queries. Link bench is social graph transaction processing. My test host was on AWS. I artificially reduced the amount of RAM on the host to increase the IO stress. Servers used EBS. All the test configurations I've used are now on GitHub. And I modified RocksDB to disable this feature called intra L0 compaction because it got in the way of measuring things. I'm not going to describe these in detail here. They're all in GitHub, but more than 14 different configurations for MyRocks, about 10 configurations for InnoDB, In some cases, each configuration builds on the next one, and I've tried to list the path on how that's done here. So let's start with an IO-bound insert benchmark. And the first phase is just loading the database. So this is loading 500 million rows into MyRocks. For the various configurations, I'm only listing the average insert rate. So I'm hiding a lot of details on variance and response time. And then I've classified the configurations into those that make things better, meaning they improve throughput by more than 5% compared to the configuration they build upon. Those that make things worse, so they reduce throughput by more than 5%. And then neutral. So neutral is something that's changes performance no more than 5% in either direction. And we can see that there's a few spikes on the curve here, which makes tuning interesting. In the middle of the graph where things fall off is the worst case is zlib, and insert rate is dropping because there's too many compaction stalls. From all the configuration options that I've selected, there were a few ones that were significantly better. And in this case, not using bloom filters makes the insert rate go faster because it reduces the CPU overhead. So the techniques I mentioned on the previous slides about reducing CPU overhead apply here. Moving this over to doing the same workload on InnoDB, the biggest one is going from the default configuration, which is the leftmost column, to enabling InnoDB dedicated server. And that is the simplest thing I can do. Just one option to set, and it provided the best throughput. But also starting with the default configuration and just increasing the redo log size, which are the CX4 configurations, just increasing the redo log size made a huge difference for this workload. And then beyond that, increasing the amount of I/O that the server could do was also a good deal. I tend to set far more options than I need to with InnoDB, and that was something I've learned from collecting this data. Now moving after the load, there's a read-write phase, and in this case, the 8,000 means that the writers are rate limited to 8,000 inserts per second, and then I'm reporting how many queries per second occur under that write rate. And there wasn't that much difference between all of the tuning options for MyRocks. So this was actually, this was interesting to learn. The configuration doesn't make that big of a deal here. Moving over to InnoDB, configuration was more significant, but again, the CX1, which is the InnoDB dedicated server, just by setting one option, I get the best throughput. So all of the other options I've been setting aren't really needed. But again, the CX4 configurations, which increase the redo log, make a huge deal on InnoDB. So the second option to set after dedicated server, increase the redo log. I'm trying not to highlight the difference between InnoDB and MyRocks, but the QPS is significantly different going from MyRocks to InnoDB. What happened here? This is the kind of information that I have a lot of scripts that summarize performance results when I'm running benchmarks. Here's an example, and the key is the storage efficiency. If we look at the storage read kilobytes per second and write kilobytes per second measured by IOstat, InnoDB is doing about 10x more I/O, while MyRocks is doing about 10x more queries per second. And part of that is that MyRocks is able to fit more data in cache, but part of that is also the efficiency benefit on writes that you get from an LSM compared to a B tree under I/O stress. And so screens like this I try to summarize using one line of data per configuration, and it makes it easy for me to quickly compare a large number of configurations and guess at what might be the cause before I begin doing performance debugging. The insert benchmark, after I do the read-write with 8,000 inserts per second, it stepped down to 800 inserts per second. And again, how many reads can happen? The MyROX results here have a bit more variance than they did for 8,000 inserts per second. But there's not a significant difference in the different tuning options. It didn't make that big of a deal beyond the initial tuning options that I've suggested. For InnoDB, again, the setting dedicated server configuration CX1 makes a huge difference, and also increasing the redo log size provides a significant benefit. The other workload I run is LinkBench, and here are just a few results for an IO-bound LinkBench, just measuring transactions per second, ignoring quality of service, response time guarantees, everything beyond the initial configuration. The leftmost column provides similar throughput. So, what this suggests is tuning really isn't an issue here. Moving over to InnoDB, once you get beyond the default configuration, things were much better. And again, the InnoDB dedicated server, one option set, provided the best throughput. Nothing else was needed beyond that. So again, here, MyROX throughput transactions per second is over 7,500. InnoDB doesn't reach 6,000. How can I explain why that's different? I/O efficiency, again, is the reason. Our RKBPT, storage read kilobytes per transaction, is about 2x larger for InnoDB. Storage kilobytes written per transaction, WKBPT, is more than 15 times larger for InnoDB. So InnoDB is doing a lot more I/O per transaction, and that explains the performance difference. So if I had to evaluate the configurations for the I/O-bound workloads that I shared and the CPU-bound results that I listed in the appendix of my talk, just listing out the configurations that were better and those that were worse, and then try to see if there's patterns. It's difficult in some cases for MyROX. Configuration 14 disables bloom filter. In some cases, disabling bloom filters was useful. It shows up for insert benchmark, for which there were compaction stalls. Disabling the bloom filters was helpful. Insert benchmark does range queries, does not benefit much from the bloom filter. So it makes sense that the bloom filter can be disabled there. LinkBench did not run into compaction stalls, so it's harder to judge the impact of the bloom filter in that case. The other, so there are, if we compare this slide with the slide that lists the configurations and the slide that listed my tuning advice, you'll see that many of the configurations that follow the advice I offered about which things to set show up in the better column, although it's not as obvious here as it will be for InnoDB. For InnoDB, configuration 1 is InnoDB dedicated server, and it's always an improvement. And then the 4, 4B, 4C configurations are increasing the redo log size. Again, that's always making InnoDB better. So it's fairly straightforward here, how to tune InnoDB. So I will save the rest of the time for questions, whether here or later. I write a lot about my work, both on blog posts and on Twitter, and there's a several places for discussing RocksDB performance and efficiency if you have comments or questions. And thank you for listening to me.
Thank you very much, Mark, for the great talk. Any questions? You can raise hand in Zoom.
Pinar, is there a way to share a link to slides?
We will share it like after the workshop. We plan to share the talk and the slides.
Okay.
Mark, if you have a link handy too, you probably could just dump it in the Slack channel today.
Is there a separate Slack for DBTest?
Yes.
Okay. I will do that.
I can also, like, I just enabled chat for Zoom too. Like, if you want, you can also do that because the talk is over. So.
Okay.
Now, Mark, maybe a quick question. So you mentioned the dedicated server option for InnoDB several times. Do you know what is this kind of an auto tuning, or do they do things dramatically different with looking at threading, or do you have an insight there?
So my memory on it is imperfect. It's well documented, all of the features that they set. The most significant thing that they do is they make the redo log large, and it's the size of the redo log is set is derived from the size of the buffer pool. So the more memory the server gets, and that makes sense. But that's the most significant improvement that they're making. It's just they're making the redo log big, and they're setting several other options. Nothing magic. It's really, I would say, a best practice. They're following a best practice, saving everybody a lot of time, including myself. That as part of this talk, I had to reevaluate how I was tuning InnoDB, and I realized I've been making it harder than it should be.
Right. Thank you.
Any other questions? I was also wondering, like, you have this is like a bare metal setup, right? You don't have any virtualization or anything in this test.
So I was using AWS servers. They are set up by the software called DSI that the next speaker or speakers.
Okay. Got it.
And DSI follows a lot of best practices, some that they discovered on setting up the server to minimize variance. I have results from servers at home that are bare metal, but they're much smaller, and so I'm not sharing those results here.
Okay, thanks. Anyone else? If not, I mean, I have one more question to you. I mean, we have discussed in different conferences about computational storage, but like how in the kind of systems you are analyzing, like, do you think it makes sense, or if it makes sense, like what kind of things can be pushed down to the storage side? Like, can we do compaction near an SSD maybe in the near future?
So, well, when I was at Facebook, we had the ability to deploy such hardware. But my perspective was it was going to be more successful on the big data side than on the small data side. where the real CPU overhead is the compaction bottleneck, I would say, from high in the LSM tree, so level 0, level 1, and level 2. So for RocksDB, I like the disaggregation approach, and Rockset is already, as far as I know, Rockset uses this in production by, they can offload compaction to other hosts, and it's a nice property of the LSM tree that you can generate the new sorted runs elsewhere, and then as long as you're able to share storage in some way, the compute nodes can pick up the new sorted runs. And that's something that works even when you don't have root access to the hardware. So if you're using the cloud as a customer, you can make that work.